Welcome back, everyone, and today we're going to start with a new lesson for building terrains. And when building terrains, first thing we're going to do is build a plane, like a flat plane, using the TriangleStrips. So that'll be our first thing to do, and then we're going to bring in Perlin Noise to actually give the points in our plane height. So this way we can start creating hills and valleys. So that's going to be what today's lesson is about. Before that, we're going to fix a bug that exists in our camera.js file. So if you open that up and go to the update view matrix function, for me it would be line 48 and 52. The order of rotation was wrong. I had it rotate X, then rotate Y. And that actually gave the camera control a slight glitch when you're behind a model. Everything was in reverse at that point. So it was a little glitchy, and it took me a while to really figure out that the order of operations was wrong. So this little fix, just put rotate Y, then rotate X, and that would actually make the camera work perfectly no matter what rotation at whatever place you currently are in the orbit of an object. So that is the first fix. And now, after this, create a new file called terrain.js. And now we're going to start building our terrain function. Now with the terrain class open, or when you start writing it, we're going to have our usual two functions: create model and create mesh. And let's look at create mesh on line 3. And we're going to pass in our GL context. We're going to pass in the width of our plane, the height of our plane, and the row length and the column length. And we have a new property called keep raw data. Now we want the size of the terrain, so we could choose how big in units that we're going to make the actual terrain, and then our length and C length is how do we divide it up? Like how do we subdivide this quad? Because we want this big massive quad to be cut up into small little quads. So if you look at line 2, you'll see that we're predefining it as 1 by 1 width and height, and we're going to subdivide by 3. So that's what's going on there. So that's going to be our default plane for now, because we're going to start small and then we're going to build up to a much larger plane and more detailed. So to start off with on line 4, we got the R start and C start, row start and column start. And I'm starting it where the plane is centered on the origin. That's why I'm doing width divided by -2, because I want it to be halfway to the left side. So this is fine just for now for this for prototyping. But down the line, if you're going to make terrains in chunks, it's actually better if R start and C start is actually 0, 0. So this way you can build everything starting at the origin, and then since you know the width and height, you can then build the next one at a different start, or build everything at origin and then move things around in whatever grid pattern you want. So for prototyping, we're just doing this because we're only creating one patch of terrain. But just remember, in the future, if you're going to do this, you might want to start at 0, 0. So I just want to make that little extinction there. Then we have line 6, and we're calculating how many vertices we need. So that's the vertice length, like how much. So we just times R length times C length. And then the next two lines, we do C inc and R inc. And it's just how to increment for all the points. So if I'm going from column 1 to column 3, because we're dividing into 3 pieces, how far is each step going to be based on the total size of the plane? So that's what the increment is. It's just how do we subdivide the plane based on how many rows and columns we want. And then line 9, I have the current row, current column, because we're going to keep track of what current row and column are on, because I'm not doing this the traditional way of doing it. So segueing into that, on line 15, you'll see I have a for loop, and I'm looping between 0 and total vertices. So I'm going to create a single array, the avert, that will exist on line 9, and I'm going to build all the vertices from beginning to end. Now, typically when you create a grid, normally you would see a programmer do for loops, 2 for loops, one that does the row and the next one that does the column. So you create, you have a sub loop inside a main loop. And here I'm not doing that. I'm actually having a single loop, and I'm actually calculating basically the X and Y or the row and columns at every loop. It's just a different approach. To me, it seems more efficient instead of having a loop that generates loops. So this way, if there's if it's a really high grid that you're trying to create, you end up starting up and shutting down a lot of loops. And so for efficiency's sake, I kind of just start up one loop and just keep going. And just instead of, I'm kind of hoping that the math to calculate the row and the column is less intensive than starting up and closing down boatloads of loops. So it's more, I'm doing this more as an efficiency thing, and by calculating it, I'm actually going to be able to do other things within a single loop as well. You'll see this as the lesson goes on. So I'm just showing you that I'm doing this in a different approach. It's not necessarily the best. I don't know. I can't say if it's the best way. I can actually say it's probably slightly more complicated in the way you have to think how it works, because you have to think of two loops combined as one. So you kind of have to track things with variables, and you got to do math to actually keep track of where you're currently at. It's definitely easier if you had a nested loop. So just take that into consideration, because you can always rewrite this to something that's easier just by using nested loops. But for now, we're going to do a single loop that calculates like a virtual nested loop. So, and then on line 20, we actually just push our 3 points in our vertex for the specific point in the grid. So we're just passing in the X, Y, and Z by using all the values that we've calculated in the start of this function. And then we just go into line 25, which we actually then pass it into our, create mesh VAO structure, and we just pass in an avert, and we're going to do a draw mode of points. So we're going to just draw points for now, and then we return the mesh. And after that, we go into our viewer.html page, and you'll see that on line 22, we're going to put in our terrain.js file. You'll see that our onload event is very simple, and on line 42, I commented out the resources setup, because we're not loading resources. And this is a file that's continuous from our previous lessons where we're loading in a video texture. So since I want to keep the same structure, I just call the onReady event. Just as soon as the load event happens, call the onReady function right away. And now we're in there, we're actually pretty simple. It's bare bones. The only big difference here really is line 56, is that we are creating our terrain model. So after that, we go into our onRender function, and again, it's pretty simple. Probably the only biggest change is really nothing really at all, because we're keeping the same variable names and everything else. And then we're moving on to our shaders. And again, this is bare bones. We're starting very simple today. Since we're drawing in points, we need to set a point size. So on line 95, you see I'm setting the point size for the grid that we're drawing. And then on line 106, I'm setting the color of black. So that's what we're doing. And now if we go to the browser, you'll see that we have our grid, our plane, divided into 3 chunks, or technically 2 chunks really, but it's 3 pieces, or 3 sets of, 3 rows, 3 columns. And there's the points being drawn. And that's the starting of creating a plane. We got our grid of points that we use. And with that, we use a new drawing mode called TriangleStrips. TriangleStrips allows us to order the vertices in a certain way that allows us to create a bunch of triangles with less data. So normally when we create a quad, we have 4 points, but we have to repeat 2 of them to create the 2 triangles. With TriangleStrips, we don't need to do that. With 4 points, it automatically knows that it's 2 triangles, because we just have to put it in specific order. And the order is zigzagging back and forth between 2 rows of vertices. So as you have in the example here, starting on line 6, you see you have point 0, 1, 2, 3, 4, 5, 6, 7, 8. That's what we just created. Those are the 9 points. And as you can see, if we go from 0 to 3 to 1 to 4 to 2 to 5, kind of how the lines are kind of going, that is basically the pattern to create our 2 quads. So we end up creating 2 quads with 6 points, which would normally, a single quad would take 6 points. So we actually end up saving a lot of data doing it this way. So that's pretty much it. It's just the pattern of creating the index, or the pattern of which the vertices are in a specific order. Now, if you want to go to, let's say, row 2 and 3 to create quads, you would have to create something called a degenerative triangle. And that's kind of like a triangle that has no area at all. It's kind of like a flat triangle. All the sides kind of like compress into a line. And that allows you to kind of like skip into the next row to continue your process. OpenGL knows enough that any triangle that has no area, it kind of just skips. It doesn't bother using a fragment shader on it. So when we're done, we're down to 2, 5. We then just say 5, 3, which kind of zip lines right across to the beginning of that row 2, and then you can continue the process again. You do 3, 6, 4, 7, 5, 8. And in the event there was actually a row 4, you would just say 8, 6, and then you continue the loop again, processing the next stuff. And that's all it is to create TriangleStrips. This works really well with, works really well with planes, and it actually works pretty well with spheres if you use polar coordinates, because that's kind of like a grid as well. Anything related with grids, you can use TriangleStrips very quickly and easily to create tons of triangles with less data. So now that we understand how TriangleStrips works, we're going to move on back to our terrain.js file. And now we're going to start adding some stuff, because now we're going to build these connected dot points. So on line 7, I created ilen is the length of the total index values that we need. So we just want to know how many indexes do we need to actually generate for all the vertices that we're creating. So then we start at line 24, and we have an if statement. And the if statement makes sure that the current loop does not go past the ilen. So I'm using a single loop to actually create all the vertices, the grid or vertices, and I'm using it to create our index. So instead of having 3 loops in total, one just to create the index, and then a nested set of 4 loops to create the vertices, excuse me, I'm taking care of everything in a single loop. Since there's more vertices than there are index, that's why I have like a stopgap. So it just keeps processing until it stops. After that is just line 27. It just creates the pattern. It just creates the pattern. It's top, bottom, top, bottom, top, bottom. And then line 30, if we reach the end of the row, we create that degenerative triangle, which takes the last point that we just accessed and then the first point of the next row that we want to start. And that's all it really does. And it's a very simple algorithm to put together. And then line 35, we add our index to our VAO creator. And line 36, we're going to stop doing points. We're going to do line strips. So this is where you can kind of see the pattern. So now if you go back to our browser, you'll see this result, and you'll see the pattern that we created. We're zigging, zagging back and forth, and then when we reach the end of the row, we zip right back to the beginning of the next row, and we zig and zag. And that's the exact pattern we're trying to create. This would actually create all the triangles, like 1, 2, 3, 4, 5, 6, 7, 8 triangles to create this entire plane. So if you were to change the mode to TriangleStrips, you'll see this becoming a flat black square. That's it. Now we're going to go back to our terrain.js file, and we're actually going to start building our UVs, because this way we then, what's a terrain without texture? So definitely at some point you definitely want to texture your terrain with grass and rock and whatever else you want. So on line 14, we're going to add our UV array that we're going to store everything. And then line 15 and 16, we're going to create our increments. Now the idea is the entire plane is going to be one whole quad that starts at 0, 0, 0, and the other corner will be 1, 1. So we need to divide the increments by 1. Since the maximum number is 1, we're going to increment. So as we're creating vertices from left to right and top to bottom, we're going to do the incremental value of 1. So this way, the entire, like I said, the entire plane is a single texture. And then if you want to, then you can scale the textures so you can make actually look nicer. So that by that scaling is all done in your fragment shader. So now that we know the increments of our AV, we go to line 27, and all we do is just push it. So, and there's kind of like an if statement here. And the way it is like if it's not the last vertice, if it is the last vertice, you make the value 1. If it's not the last vertice, then you make it an increment of that position in the grid. And that's all we're doing for the X and Y position in our UVs. And then on line 42, we add it to our VAO function. And it's very simple, and that's pretty simple. That's the gist of it. And again, I'm doing everything in a single loop, so it's very optimized to actually kind of create all this data really quickly and in one go. Now we're going to go back to the top of the terrain file, and we're going to do some more modifications. On line 2, we're going to change the default size of our terrain. We're going to make it a 10 by 10, and we're going to subdivide it by 20 by 20. So that is going to be the new size of our terrain. It's going to be kind of big. Now on line 19, we're going to start, and we're going to use Perlin Noise to actually generate our height. And in case you don't know what Perlin Noise is, I'm not going to go too deep into it, since there's tons of videos and information online about it. It's been used since I think 1980. I think it was originally made for the Tron movie to make dynamic textures. So Perlin Noise is a random number generator, but it's unique that it actually creates a progression from one random number to another. So it kind of lerps from A to B, and that allows you to create hills and valleys instead of like these spiky points that you normally would with like a random number generator. So that's why we're using Perlin Noise, because it gives us that nice rounded thing based on how you call it. You kind of use a frequency. You kind of like a step. Like how do you want to step through this, the Perlin Noise, all the noise, and then it kind of gives you that number. So based on the frequency is how smooth and how jagged your terrain gets to be. So so that's what frequency is about. And the way I would probably describe Perlin Noise is that it's ordered chaos. Where random number generator, it's just plain chaos. Perlin Noise is ordered chaos. And you have a seed value. So let's say if you have a certain settings and you change the seed, it creates a different pattern, basically. So you can change the seed, you can change the frequency, and since it's a random number, it gives us a number between 0 and 1. So we kind of have to give it a height. So we do a -3 for maximum height. So that becomes the multiplier for our actual height. So with those settings out of the way, then we calculate the height with Perlin Noise on line 29, and we kind of use the current row and the current column, divided by our frequency to kind of step through the Perlin Noise to generate our height value. And on line 32, we change our height value. Or Z value, our Y value. We have 0.2, we just add plus H. So we're just add on our default height. We're just going to add on the height, which be some number between, from -3 that we have preset up. Let's see. So that's that. Now we go back to our HTML page, and we're going to add in our Perlin Noise. You can get this file from the GitHub of wherever this originated from. I'm sorry, I don't have the name of it right now. And or you can just get it from my GitHub page for this lesson to bring it down. Everything should be for you guys. Well, unless you already have a Perlin Noise JS file, you can use that too. So all that we're going to do is implement the Perlin Noise, and if we go back to our browser, now you see our grid now has kind of like that nice hilly patch, So now we're getting our terrain nicely put together now. So we're getting there. So now we're going to go back to our terrains, and after the loop of where we create all our arrays, we're going to create our normals, because normals are very important to terrain because we need to do lighting, and if you don't have lighting, terrains just doesn't work very well. So I looked online how the best way to do it, and there was a forum post that described something called the finite difference method, and it basically looks at the surrounding vertices of the specific vertice that you're looking at, and based on their height, it calculates kind of a perpendicular direction that the vertice you're actually working on should be pointing at. So that's the overall algorithm. So I tried to apply it to our grid. So it worked out very well. So I'm not a mathematician, so I can't explain any further than that. But it works, and I'll try to help step you through. So from line 50 to 63, tons of variables, and I put comments on describe what each one is, so I don't need to really go through it. And then we have our for loop that we're going to actually calculate. We're going to go through, because we have to go through our vertice array to pull out the heights that we just generated with Perlin Noise, and then like I said, get the surrounding areas to actually finalize the actual direction we're pointing at. So we're going to do a for loop. We're going to calculate our row. We're going to calculate our column, and we're going to calculate the position of our x and y stuff. As we scroll down, based on the position that you're currently in, like if you're at the top corner, you can't go any further, and everything else. So the next 4 if statements is really just to figure out the height of the surrounding vertices, and that's all we're doing here. Just what's the height, and based on if you're the last or not the last one, you get different values, different heights to use. I think the original C++ algorithm was a lot simpler, the if statements, but because of I'm building it's more complicated simply because I'm making a single array of floats, where the original algorithm was an array of vertex objects. So this one's a little bit more complicated simply because I need to take into account that I'm not using an array of objects to get the XYZ positions. Everything exists in one massive array. So that's why it's done this way, in a little bit more complicated way. Then we scroll down, and once we have all our heights in all our directions, we kind of just then calculate the normal. And then we just save the normal. And that's pretty much the whole algorithm altogether. And then line 104, we pass in our normal, and and then we switch our draw mode to TriangleStrips, and then we add the if statement to keep our raw data. In case we need to start debugging information, we can then if we keep our raw data, we can actually output some debugging stuff, which we're actually going to do. So if we go back to our HTML page and we go to on ready function, after the get terrain, we have that line where we actually create our model terrain. We set the value to true because we want to keep the raw values, and then we're going to add in our line debugger. And our line debugger, we're gonna give it a green color, and we're going to pass in our gmodel mesh, because that's why we need to save the raw data. So this way we can grab all the normal information that we generated, and then we finalize it. And then on our render function, we on line 85, I'm just going to render out all our normals. So if we go to our browser, you'll see all our normals being outputted as little lines. So you can then make sure that all the lines kind of go with the curvature of our terrain. So this is a nice way to help you debug some of these things that we're kind of working through. So we're almost there. We got the terrain working. We got all normals working just right. Now we have to move on to actually adding lighting, because once we get at lighting, then you can kind of see the difference between high and low points in the terrain. So let's go back to our HTML page, and we're going to start modifying our shaders. So we're going to hack in some simple diffuse lighting into it. So as you can see in line 102, we're going to create an output variable that goes to our fragment, which is going to be our diffuse angle. Because in the previous lesson when we dealt with lighting, remember we take the position of the light based on the direction of the normal, and then we kind of create this number between 0 and 1 that tells you how strong the light is, or basically the angle in a normalized way. So that's really what our diffuse angle value is, in case you didn't remember. So that's all we're doing, just getting the angle between, like I said, the normal and the light. And then instead of bringing in the light position, we're just making it a constant in our vertex shader. In the end of the day, in real life, you're going to want to pass in the light direction dynamically. But for prototyping, that's what we're going to do. You're going to see where the light is once we have it all rendered. So if we move into our fragment shader, line 116, we're going to bring in our diffuse angle, and we're going to do some more constants. We're going to create our light color and our base color. And line 123 kind of just calculates everything. It takes our light color times our diffuse angle, which is basically the strength of the light, and then we're just going to add that light color to our base color. This is going to be slightly different than how I think we did it in the previous lesson. I think I just multiply everything. In this case, because I'm not adding ambient light and then adding diffuse light, I'm not doing a bunch of stuff, so I'm just taking the basic color, which is red, and just adding on light color to it, just to make it brighter. And then, we just output everything to 125. And if you go to our browser, there you go. You'll see our terrain now is that you can actually see the curvatures a lot better because the lighting kind of accentuates, the curvature a little bit. So this is kind of neat. So now you have terrain. You can color it. It's all sweet and good. So, I want to make it more like pixelated. And so I looked online for a while, and I found an algorithm for shaders to kind of make the terrain more pixelated, more for that kind of style. So if we go back and go to our shaders, we're going to comment out a couple of things. We're not going to need our diffuse angle anymore, or our position light in our vertex shader, but we are going to need to create our world position. So on line 102, we have an output value of our world position. And on 109, we just calculate a world position. It's the same thing that we're doing in 112, but we're just saving just the world position. That's about it. In the ideal world, you would probably do world position and then apply that to GL position, so you're not calculating it twice. But just for quick prototyping, this is fine. But for you want to optimize this in real life, you would reuse world position in your GL position. So this way you save on one less matrix calculation that you're doing. And then on line 118, we bring in our pose world, and we're going to bring in our constant light position because we're going to do everything here. And then on line 127, we're going to generate new normals. Now, we're not going to use the normals that we created. We're going to create normals on the fly. And I actually don't understand how this works, to be honest, but you need the world position to calculate new normal directions. So line 127 generates us new normals based on world position. And I forget what df, dx, and does. It does like a differential type of equation on the x and y position. And then line 128 is basically the same thing we were doing before. We just getting the angle between the light and our new normal. And then we use the world position of the pixel instead of the vertice. And then we get the different angle, and again we just do the same thing. And if you go back to the browser using a new little algorithm, you see things are a little bit more. I don't want to say pixelated. I forget what this probably is, what's called. But it gives it that nice look, kind of like the wireframe. You can kind of see all the triangles in it. So this is kind of a nice look if you wanted to kind of texture things without with an actual texture. You just want to do coloring, but to kind of give it this kind of like style, like low poly. That's the term I'm looking for. A low poly kind of look to it. So that's what we're doing. Is we're creating a low poly, and we're doing it by generating normal values on the fly using an algorithm I found online. And that's pretty much it for our terrain. And that's all we're going to do for this terrain. And that's all to it. You can go out and play around with it. And the last things we did was like 3 lessons of texture. So I'm not going to texture. I'm going to show you how to texture. You guys should know how to texture by now. And we created the UV values, so you have them there in the fragment shader and in the GPU, and everything's all set up ready to go. But I will show you how it looks like when we actually put a texture on it. So there's our terrain, but textured with our lighting, and that's it. It looks pretty good. It looks great. So yeah, there you go. We have created terrain in our virtual space. We have sky maps. We have people. We have a lot of things. So there's a lot to do. So hopefully down the line, we'll start doing something with this. But I think the next step I'm going to move on to is WebVR, and really get into virtual reality a little bit, and then start doing some other things. But hopefully soon we'll start getting into actual game development and constraints and whatnot, or colliders, I should say, not constraints. So hope you had enjoyed the lesson and had fun building terrains. See you guys at the next lesson.